So guys, today is going to be sort of a catch-all, a sweep, if you will. We've obviously talked about titration last year. We're going to come back and revisit that today. Cody, did you guys titrate at Tim? You did? Okay. So guys, we're gonna talk titration briefly. But then guys, there's a couple other things that we need to talk about. We understand, I think, molarity, solution concentrations. But guys, there are two things relative to that we need to talk about. One is you're going to find that there are multiple ways for us to think about solution concentrations. It's not conceptually difficult. You just need to understand it. And then guys, in addition to that, you also need to know how to prepare solutions at requested concentrations. And we're going to talk about that. So we're going to talk about molarity. We're going to talk about solution creation through a process called dilution. Then we're going to touch briefly on titration. We're going to be done early and you're going to get some homework done. The homework assignment is short. And then guys, Thursday is your first test. Can we dig in? Okay. So guys, with that said, the place we need to start there is, and I don't think you need to write this down. But guys, we're all clear on this, right? When we talk about concentrations of solutions, and we've been doing this throughout the year, we think about molarity. And molarity is just moles of solute, liters of solution, right? Are we comfortable with that? Okay. So guys, with that said, what we need to talk about then is this. There's actually, and I think you're going to want to write this down, there's actually two ways that we can think about molarity. And we've seen a couple homework questions already that have alluded to this. But guys, we need to be absolutely sure that we're clear on this. So one way that we can think about molarity is simply by solute concentration. And I'm going to give you a couple examples. So guys, when we think about the molarity of the concentration of a solution, one of the things we can think about is just the concentration of the solute. So for example, you grab a bottle and it says 1 molar NaCl. And from that information, you know that there's a mole of NaCl dissolved in a liter of water, 1 molar NaCl. Or you could grab another bottle and you could say 1 molar calcium chloride solution. Again, a mole of calcium chloride, liter of water, off you go. Where's my other pen? Aha. All right. But guys, here's the point. Why do we care about this? And the answer is this. So guys, you know that the freezing point of water is 0 degrees Celsius. Okay. Here's the question. These two solutions, will they freeze above, below, or at 0 degrees Celsius? Is that Josh? You're not Josh. You don't even look like Josh. Do you know Josh? Have you seen Josh? Okay. If you see him, tell him we miss him. Where do I sign? Oh, wait, right here? Perfect. Thank you. See you. So guys, let's try this again. So these two solutions, above, below, or at 0 degrees Celsius, where do they freeze? Below. And if you don't remember why, guys, the idea is this. This is what ice looks like. And in order to get water to freeze, you need to slow the molecules down enough that they can form these interactions represented by the purple sticks. Those are intermolecular forces. And if the molecules are moving faster than the freezing point, these intermolecular forces are not strong enough to get these molecules to stick together in this ordered pattern. And that's what we call melting, and that's a liquid. But then remember, guys, if we dissolve salt If we dissolve salt in the water, if we dissolve salt in the water, the salt gets in the way of the formation of these structures, and consequently we have to cool it down more to get it to freeze. Do you remember that idea? Okay, so now the question is this. Are we sold on the idea that these will both freeze at temperatures below zero? They will also boil at temperatures higher than the boiling point of water, because for the same reason that it's harder for it to freeze, it's harder for it to boil. Freezing point down, boiling point up. You guys good? Here's the question. Will they freeze at the same temperature? We know that they'll both freeze below zero, but will they both freeze at the same temperature? The answer is no. Which one will freeze at a lower temperature, the sodium or the calcium chloride? The calcium chloride. And guys, we need to understand why. And the reason why is because that second solution is more concentrated. You're going, wait a minute. They're both 1 molar solutions, but they're not. Yeah, and guys, that's what I want you to do. Down below here in your notes, skip down a couple lines, draw yourself a couple beakers, put some water in your beakers, and then guys, the one on the left is going to be sodium and the one on the right is going to be calcium. Guys, please, in those beakers, write the species that are present in those aqueous solutions. Have you noticed that one of my great joys in life is drawing beakers? Yeah. And I'm horrible at it. I'm a left-handed guy drawing on a board. I'm awful, but it still makes me happy. All right, guys, so what have we got in the left-hand beaker? Sodium ions and chloride ions. Guys, what do we have in the right-hand beaker? Calcium ions and chloride ions, but 2 of them. So guys, now let's talk about this. Because while yes, we can talk about the concentrations of the solute, we can also talk about the concentrations of particles. So now do this. Guys, above your beakers, write down the molarities in particles. What is the particle molarity in the left-hand beaker and the right-hand beaker? Left-hand beaker, what's the molarity? 2 molar. Right-hand beaker? 3 molar. Guys, the idea is that when these solutes go into water, they completely break apart into their ions. And because calcium chloride is CaCl2, that solution is actually more concentrated in particles than the one is on the left. And consequently, it behaves differently because the freezing and boiling points of these solutions, and we'll explore this in lab, but guys, the freezing and boiling points of these solutions are not dependent upon the concentration of the solute. It's dependent on the concentration of particles, and the one on the right is more concentrated. Do you get the idea? Okay. So guys, that then is the other way that we think about molarity is particle concentrations. Go ahead. Yeah. They do not. Yeah, and Caleb, I'll be honest with you. So what we're talking about here are what are called colligative properties. Okay, so using that in a sentence, a colligative property of water is that you add salt to water, the boiling point goes up, freezing point goes down. There are other colligative properties, but by definition, a colligative property is a property of a solution that only depends upon concentration and not what the solute is. And it drives me nuts because honestly, in my mind, it should matter what's dissolved in there. Your example, bromine and chlorine are not the same stuff. They have different electronegativities, they have different masses, they have different sizes, but it turns out they behave exactly the same. So if you had a 1 molar solution of sodium bromide, and if you had a 1 molar solution of sodium chloride, they would boil and freeze at exactly the same temperature. And I hate that because I don't know why. It doesn't make sense to me. It seems like they should be different, and they're not. I know that there's explanations for it, that the reason that they change their boiling and freezing point is the interference of the ions, and it shouldn't matter. But it's still, I don't like it. But the answer is no, they'll be the same. So, you guys settled on this? Does this sit okay? Okay. So guys, moving along then, what we need to do is we need to talk about sort of the next thing on our to-do list, which is how to form solutions. Guys, you haven't, I'll be back. I may as well show you. So guys, it's time to peel back the veil and let you see the wizard. So, if you've been staying up late at night asking yourself the question, where do acids come from? This is the answer. So, guys, when you go into lab, I'm sick of these. When you go into lab and when you grab a bottle of 1 molar hydrochloric acid, guys, these acids obviously just don't appear out of thin air. So where do they come from? And the answer is, I make them. I prepare all of your solutions that you use in lab. But then where do those things come from? And the answer is, I buy them from supply houses. But the trick is this. For example, hydrochloric acid. It is ridiculously expensive to ship. The shipping is actually 3 times the cost of the actual chemical. Because you put a bottle of hydrochloric acid in the mail and bad things can happen. So you need these things to be well packed and well sealed. And it's actually really interesting. They come in a styrofoam container that's then put inside a box and then put inside a bigger box that then is stuffed full of vermiculite. And then they seal that up and then they hand it to the UPS guy and wish him luck and send him on his way. But guys, this stuff is expensive to ship. So consequently, to get around that, it's no more expensive to ship 12 molar hydrochloric acid as it is to ship 0.01 molar hydrochloric acid. In the eyes of the hazardous materials people, it's all hazardous. So, guys, when I buy acids, I buy them in their saturated forms. Guys, this is the strongest that hydrochloric acid can get at room temperature. This is it. This actually saturates at 12 molar. Yeah, it is. It's 12 molar. So this is saturated hydrochloric acid. If you were to cool it down, you could make it stronger, but at room temperature, that's as good as it gets. So guys, when I make your hydrochloric acid solutions, what I do is I start with the concentrate and then I dilute it down to the solutions that you need. Understand, guys, bases are different. Bases, right? Bases are solids. They're salts. So for example, this is sodium hydroxide. So when I make sodium hydroxide solutions in other bases, they start as solids. But all of the acids start as, all the strong acids start as concentrates. The weak acids actually could start as solids as well. chloric acid 12 molar, sulfuric acid 18 molar. Terrifying stuff. But guys, here's the thing that's interesting. 27 years I've been teaching chemistry. This is my second bottle of HCl. That's how long this stuff lasts. Guys, this is literally the second and a half, because when I got here, there was, in 1993, there was half a bottle left, and I used that, and then I bought a new bottle, and that bottle lasted me until last year. So I'm now on bottle number 2 of HCl that I've bought in my 27-year career. Guys, there's an efficiency to this because we buy these things as concentrates. So all of that to say, you need to be able to think through the logic of how. So guys, we go into lab and we need 250 milliliters of 0.01 molar HCl. The question is, how do we make it? Guys, to be honest with you, the answer is I cheat. When you go into the stock room next time in lab, you know how you guys walk into the stock room and you go left to get your keys? Go right, and there's a board right inside the door, and on that board is a laminated green and white sheet of paper that actually has all the dilution ratios for all of the commonly used acids that we use in lab. So if you need a liter of 1 molar acid or 2 molar or 0.1, it's all there. So guys, frankly, I cheat, and I just get it off of there. You need to know how to do the math. So, guys, write this down with me, and then we're going to play with this a little bit. So what we're talking about now are, you don't need to write this down. This is conversational. So what we're talking about right now are what are called dilutions. Again, the idea is most of our solutions are bought in concentrated form and then diluted down to the concentrations we need. Guys, these calculations are done using what is called a dilution ratio. This is not on the AP equation sheet. They expect this to be common sense enough that it's just part of your thinking. And it goes like this. So guys, it says molarity I times volume I is equal to molarity F times volume F. And obviously, well, not obviously, obviously, that's initial and final. So guys, how do we use this equation? Well, let me offer this to you. Stock sulfuric acid solution, 18 molar. Guys, we actually had a 2-liter bottle of this spill in my lab 9 years ago. It's actually a really sad story. So guys, 9 years ago we built the new school, right? You guys were what, 7? Okay. So guys, it was a testament, frankly, to the magic of Utah County. You guys don't know, well, some of you know the difference because you haven't lived here your whole life. But guys, things happen in Utah County that don't happen anywhere else on the planet, and it's awesome. So what happened was this. You probably know that we built Orem High School, the new building, while we were still occupying the old building, right? And so we were teaching over there for 2 years with no parking lots, because this used to be our parking lot, and they built the school, our new building, in the parking lot, right? So the only people that could drive were seniors. Sophomores and juniors weren't allowed to drive to school because there was nowhere for them to park. They built this parking first, and that was the only parking we had. So we built the school while we were in that building, and literally, guys, one day, the last week of school, one day, and this was organized ahead of time, guys, we moved the entire school from that building to this building in one day. Desks, books, tables, chairs, teacher supplies, my entire chemistry stock room. got moved in one day. And guys, the way that happened was all the local wards came. Seriously, it was magic. They made this a ward work day. And guys, we literally had hundreds and hundreds of adult volunteers that took a day off from work, and it looked like ants moving things back. It was unbelievable. It was really, really cool. This was the hard part. And forgive me, maybe some of you, I don't even know his name, but he was from the local wards, and maybe you know him. But there was an elderly man that used to be a chemistry professor over at BYU. He was long since retired, but he took a special interest in helping me move my stockroom because he was a chemistry professor. And he was, I think, probably progressing into he had some tremor, Parkinson's kind of things. And he grabbed a hold of this tray, like that tray over there by Elise. He grabbed a hold of this tray, and he was carrying it all the way across, and then he even made it up the stairs with this tray. And in that tray, there was a bottle of concentrated sulfuric acid. And he went to the front of my lab, and he went to set the tray down, and it slipped. And it wasn't over the counter, and it landed on the edge and fell over, and that bottle of sulfuric acid hit the ground and shattered. And it got on him, and it got on the floor, and it got on the front counter and it was crazy. Like all of a sudden, all of the administrative radios, "Where's Knappenberger? Get him up here." I mean, it was like, I didn't know what happened. And I just ended up bathing everything in baking soda. I mean, him and the floor and the counter. And they actually ended up having to retile the floor. If you look over there, when you're in lab next time, there's actually tile up in front of the floor that are a little different color. And if you look at the counter, they actually chose not to fit. There's stains on the front of and it's because, anyway, so all of that. This stuff's terrifying. Yeah. He didn't get that. It wasn't like he was hurt, and he felt horrible, and anyway, tough day. So, guys, bottom line is this. How do I do that? So we go into lab, you go into lab, and I typically do this work for you. And guys, for this lab, we need 1/4 of a liter, 250 milliliters of 0.1 molar sulfuric acid. Guys, the pH of 0.1 molar sulfuric acid is less than 1. It's like 0.7. We will do the math later. But guys, if you get 0.1 molar sulfuric acid on you, you're going to be hurting really fast. This is no screwing around stuff. The question is, how do I make it? We're going to do the math. Join me. So guys, in order to do this calculation, it goes MIVI is equal to MFVF. Now here's the way the math goes. Guys, we need to know the initial molarity of the solution. That's 18 molar. Now, what we want to know is what volume, this is our X, what volume of that 18 molar stuff do we need to finally create a molarity of 0.1 molar, and we need 250 milliliters of that solution. And guys, whatever units you're given are the units you can use. If you're given liters, fine. It just means your answer will be in the units that you were given. So the molarities cancel. We're left with milliliters. So we have 0.1 times 250, and then divided by 18. What do we get? Through 2 significant digits? You starting to get the idea? Guys, this is 2.5 liters. I think. It is. Guys, this is 2.5 liters. This is 2,500 milliliters. Guys, this is 2.5 liters. And this is a very typical dilution. We need a quarter. This would get us through an entire day of lab. 250 milliliters, 0.1 molar salt. I know this is hydrochloric and not sulfuric, but the analogy stands. Guys, in order to make this solution, I need 1.4 milliliters of acid. It's almost so small it's hard to measure. And I take that 1.4 milliliters of acid and I dilute it up to a quarter liter, and I've got enough acid to supply everybody for a day. Because that's why I've only needed 2 of these bottles my entire career. Same thing with, well, frankly, longer with salt. I've never bought sulfuric acid because we use it so much more infrequently. Yeah. And that's what we need to talk about, because you have to know this for the test. We're going to write this down. So guys, don't forget this number right here, 1.4 milliliters. And you have to know this. So guys, on the test, you are going to see questions that are like this. How would you make this solution? Guys, write this down with me. You've got to do this right. Ready? Step 1 is going to become the running joke in this class. Step number 1 is this. Put on gloves, goggles, and apron. You have to write that down, or they will not give you credit for this question. Seriously, that's their nod to lab safety. Ironic part is you guys have been doing labs with me for what now, a year and a half, and we've never seen gloves or aprons, but you get the idea. Okay, now guys, this is where this gets really detail oriented and really specific. So guys, let me introduce you to a new piece of glassware. This is what is called a volumetric flask. This is the way that you dilute solutions. Guys, for those of you that are in lab, you know that anytime we use a piece of labware to make a measurement, what do we do first? Calibrate it. These are stupid expensive. This is like $30 to $40. The reason it's so expensive is you buy it pre-calibrated. They calibrate these for you. And here's the way this happens. You can't read this, but on the side it says 250 milliliters. Guys, the only thing that this piece of glassware can do is measure 250 milliliters. And here's how they do it. What they do is they don't calibrate this by volume, they calibrate it by mass. And there's a machine that does it, but the way that it the flask, what they do is they fill this up with water, but they know the temperature of the water, therefore they know the density of the water. Starting to sound familiar? Therefore they know the density of the water, therefore they know exactly how much 250 milliliters of water will weigh. And so what happens is a machine does this. It puts the flask on a balance and it fills it up with exactly that mass of water. Now guys, you'll notice the neck of this flask is very long. The reason is because they can blow this glass accurately enough that they know that 250 milliliters of water is going to land somewhere in here. If the bulb is a little bit smaller, it'll be higher. If the bulb is a little bit bigger, it'll be lower. But then guys, literally, and I don't know if you can see this, what happens is a photo eye actually finds that 250 milliliter mark, and then it laser etches a line right at 250 milliliters. Can you guys see it? There's actually a line, and if you listen, you can hear my thumb catch on it. Because there's actually a laser etched line right there. And that's all that this flask can do is measure 250 milliliters. There's no other marks on it. That's why they're so expensive, is they come to us pre-calibrated. Get the idea? Okay, so guys, this then is how you need to proceed with this. you are going to partially fill a 250 milliliter volumetric flask with distilled water. If you put water, you get no credit. It has to be distilled water. You okay? So guys, what we've got then is we've got well, here I can show you. We've now got a volumetric flask with some water in the bottom. Okay, now what we need to do is we need to get our acid. 1.4, is that right? Okay, so now we do this. Measure 1.4 milliliters, 18 molar H2SO4 using a pipette. That's how we accurately measure small volumes.
How do you know, like, how many significant digits to go?
3, 3, 2. So 2. Is that okay? Go ahead, Rob.
So with pipette.
Yep.
Because there's many different there's those little cheap throwaway plastic ones.
Those are the ones I use. Yeah.
Do they not dissolve I think they're plastics.
Yeah, no, they're made of cross-linked polyethylene. No, so they're pretty impervious to this stuff. They do pretty well. Yeah, even 18 molar. Okay, so guys, measure out. Now this is where you got to be careful. Literally, slowly add the acid to the flask. Now guys, here we've got to talk. You will see questions in multiple choice on this on the test. Not this, but this concept. Guys, you always add, and you may want to off to the side write this down as an overarching thought. I'll say it in the positive. You always add acid to water. You may just want to scratch that down somewhere. You always add acid to water. You never add water to acid. Let me explain why. Guys, when you put this H2SO4 into water, this is the chemistry that takes place. The H2SO4 beats the bejinkers out of water. This is not dissolving into the water. This is reacting with the water. And guys, this is an amazingly violent exothermic reaction. It is so exothermic that sometimes it boils. It's terrifying. I've had it happen. But guys, even if it doesn't boil, as you add the acid to the water, this will get hot to the touch. So much so that sometimes you can't stand to touch it. Now guys, here's the problem. Imagine that this was acid. I did it wrong. Imagine that I put a bunch of acid in here and then added water. If this boils, what's coming out the top of the flask? A lot of acid. You're going to get hurt. But if this is water and I add a little bit of acid, if it does boil over, what comes out? Mostly water, and that's less dangerous. So guys, you always add acid to water and not the other way around. So if anything does go wrong, the majority of what's coming out is water and not acid. Okay? All right, so now that we've slowly added the acid to the flask, we now have step 5, and step 5 is simply fill flask to line with distilled water. So fill it up to 250, you're done. That's it. So guys, those are specifically steps that they're going to hold you accountable for. Yes, you have to put goggles, apron, and gloves. You guys okay with the idea? All right. So guys, we've got one more thing to talk about. Bump, 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 and we're done for the day. Titration. Josh, have you done titrations before? Did you do these? Okay. So guys, based upon the idea that we all have some background in this process of titration, what I want to do is I want to offer to you maybe some strategies for solving these problems. And then we'll solve one together and put it in context. So let me just give these to you and then we'll dig in. So guys, when you're solving titration problems, always, always, always write balanced equations. Then guys, what you're going to see is that many times this problem-solving procedure becomes, almost always, it becomes dimensional analysis. When you're doing that, make sure that you're getting starting point and goal clearly defined. Then guys, thought number 3, in this dimensional analysis, you will typically be looking for mole-to-mole ratios. So if you're not sure where to go, move towards a place where you can implement a mole-to-mole ratio. And then guys, finally, what you're going to see in these problems that'll be different from the ones that you did last year, sometimes your goal will not be directly identifiable. You'll take one step, which will then lead to what we think of as being external calculations that will then allow you to fine-tune your goal. So guys, we're going to solve one of these together. We're going to draw some pictures as we do. And then you're going to have time to work on your homework. Can I go on? You ready to go? Here we go. So guys, it says this. You're given a sample of a solution. It's water. But guys, you know that there is chloride ion dissolved in this water. So you titrate it with a silver ion solution of known concentration. And the question is, how much chloride was in the sample? So guys, before we even get into solving this problem, and if you want to write it down, I'll pause for a second. Guys, there's all sorts of chemistry that we need to talk about. But again, the question says this. How many grams of chloride, how much chloride is in a sample of water if it takes 20-ish milliliters of a silver ion solution to react with all the chloride in the sample? So you get a job in a research lab and you have somebody they sink a well and they want to know if this well is fit to drink, and they're concerned that there are elevated concentrations of chloride in the water. And so they bring you a sample of the water, and the question is, how much chloride is in this sample of water? Well, guys, in order to figure that out, you've got to be able to tie up that chloride in such a way that you can actually figure out how much it weighs. And this is the way to do it. You guys all caught up? Can we draw pictures? Okay, so guys, do this first. Skip down probably like 5 lines or so. And then guys, what I'd like you to do is I'd like you to draw a picture of what this titration would look like. Understand that on the AP test, they will ask you to draw lab setups. They will give you a virtual collection of lab equipment, and they will say, draw the setup. So guys, draw the setup. Labeling as much as you can. If you were carrying out this titration, what would your lab bench look like? Do it in your notes. Here, let me leave this up for now. Can we draw together? Okay. So guys, when you're doing drawings like this, don't get terribly carried away with trying to be, well, unless you are artistic. Guys, really, schematic drawings are just fine. So typically when you're doing stuff like this, you're going to have a ring stand. It's not wrong to draw yourself a magnetic stirrer. Then, on your ring stand, you are going to have a burette. On your stirrer, you're going to have a beaker. But then, guys, the question is this. What goes where? These are the fundamental components of a titration. You've got a burette, and you've got a place for your other component in the titration. But guys, which goes where? What's in the burette? Silver ion. What's the molarity? 0.1. Okay. So guys, in the burette, we've got our 0.1 molar silver ion solution. So what is then in the beaker? Our chloride water. This is our sample. This is the thing that we are titrating. And guys, that's it. We don't even need an indicator for this titration because it's not acid-base. So guys, now that we've got this, we need to talk about how on earth do you do this? So this isn't silver, this is actually white gold, which is different. But guys, imagine that my ring was silver. We need a silver ion solution, right? So if I want to make a silver ion solution, can I just take a chunk of silver, huck it in water, and create a silver ion solution? No. So guys, there is no such thing as a silver ion solution. But now you're going, wait, they just told us silver ion solution. There's something missing. The other ion. But guys, what would be a wise other ion to use in this case? How do we get silver to dissolve in water if silver doesn't dissolve in water? Get a salt. Guys, that's what we're actually doing here. This is not silver dissolved in water. We need a silver containing salt that is soluble in water. Guys, in lab, the one that we like to use is silver nitrate. So, why is silver nitrate a great choice? Nitrates are always soluble in water. And if nitrates are always soluble in water, what does that always make them? Spectators. And that's why we don't even include it in the conversation, because we're smart chemists. And we know that it makes sense to use a salt that has a negative ion that is always soluble, so it's always a spectator and it gets out of the way and it doesn't muck with the chemistry we care about. Good? Okay. So guys, this is actually then a silver nitrate solution. So now let's go back and talk about this. Why did we choose silver in the first place? Because it precipitates with chloride. Guys, we are trying to find the amount of chloride. And so in order to do that, we are going to leverage the idea that we can get chloride to precipitate. So here then is the question. Guys, imagine this in your mind's eye. This is full of silver nitrate. And you open up, well, we should talk about this. Guys, what does silver nitrate solution look like? It is clear, and it shouldn't be. If it is, it's been out in the light. So guys, if you've seen silver chloride solution and it does look gray or black, remember this is the photoreactive stuff. Did I say silver chloride? Silver nitrate. Silver nitrate is photoreactive and it will turn black. It's why it dyes your skin. But guys, silver nitrate solution should be clear and colorless. Do you understand the difference? What does clear mean? You can see through it. What does colorless mean? No color. And guys, understand, solutions don't have to be both. So like, for example, this is a potassium permanganate solution. This is clear and purple. You see the difference? Clear means that you can see through it, and then it can have a color. So guys, silver nitrate solution is clear and colorless. This would be clear and purple. Do you see the distinction? Okay. So, let me put this away. Okay, so guys, the silver nitrate is clear and colorless. What does the salt water, or what does the chloride in water look like? Probably clear and colorless as well. So guys, now when we add the silver to the chloride, what are you going to see? Precipitate. And guys, you're going to open this up, and as the silver solution hits the chloride, you're going to see right at that impact site a white precipitate form. Now here's the question. How do you know when to shut this off? How do you know when you're done with the titration? Stops forming precipitate. And so guys, what you're going to see as this stirs is that at that impact site, at first you're just going to get tons of precipitate forming. And then that formation of precipitate is going to slow. And at that point, you're going to dial this back and let it drip. And every time a drip hits, it's going to form white solid, drip, white solid, drip, white solid, and then drip, no white solid. That's when you shut it off. So why would that drip not create white solid? What happened? You're out of chloride. The chloride is now gone. You have tied it all up as silver chloride, so you have now literally transferred all of that chloride ion into silver chloride, and you now know some important information. You know how much of this it took to tie up all of that. And by knowing how much of this it took to tie up all of that, you can then work backwards and find out how much of that there was. You understand the idea? Let's do the math. So here and here. So guys, let's set this up then. What are we solving for? What do we want to know? How many grams of chloride? So guys, we're going to go all the way to the right, and we're going to go grams of chloride. Now guys, what do we know about this particular titration that allows us to figure out how many grams of chloride we had? What do we know about this particular titration that would be an indicator of how much chloride we had? So let's do this. The more chloride we have, the more stuff we need to tie it up. So the amount of stuff we needed is the bridge to how much chloride there was. So how much stuff did we need? 20.2 milliliters. Now guys, we're doomed to failure. Because we can't get from one to the other without what? Balanced equation. Silver ion plus chloride ion yields solid silver chloride, and it's balanced. Now we have a balanced equation. Okay, so now guys, how can we get from milliliters of silver solution to grams of chloride ion? We need moles, but to get to moles, what's our bridge into moles? Not the formula mass, the molarity. See guys, because remember, this we know the molarity of. So here's what we're going to do. We're going to go 1,000 milliliters is 1 liter, and then 1 liter is 0.100 moles of silver ion solution. What that allows us to figure out is in those 20.2 milliliters of titrant, how many moles of silver were in there? But guys, why do we care about how many moles of silver are in there? Because if we know the moles of silver, we know the moles of chloride. Because what's the relationship? 1 to 1. For every 1 mole of silver, there's 1 mole of chloride. That's from the balanced equation. So now we're in moles of chloride. Now can we get to grams of chloride? Now we need the formula mass. 1 mole of chloride is 35.5 grams of chloride. And now we do the math. So guys, we've got 20.2 divided by 1,000 times 0.1 times 35.5. 3 significant digits, 0.0717 grams of chloride ion. Yeah.
So wait, I got. Oh wait, I was confused on where you got the 35.5.
It's the mass of chlorine.
Mass, right?
Yeah. You guys okay? So guys, that actually took longer than I thought it might. But we still have 10 minutes, which may actually, well, I don't know if it'll quite be enough. But guys, here's the goods.